Hi everyone, my name is Peter Deutsch,
And I'm Yuheng Yang.
and today we'll be talking about DAGguise, a novel mitigation scheme for memory controller side channels. This is a joint work between myself, Yuheng, Thomas Bourgiat, Jules Dreen, and Professors Joel Emmer and Megja Yan from MIT CSAIL. Microarchitectural side channels have become a prominent issue in the computer architecture community. While there are now many hardware and software primitives to enforce isolation between an attacker and a victim, there are still very large attack surfaces which can result in information leakage. One such attack surface is through contention on shared resources, such as a memory controller, ring bus, or SMT port. In defending against such attacks, there is a key trade-off between security and performance. While it is initially tempting to statically partition resources to disallow contention, such an approach can significantly degrade overall system performance. In this work, we focus on mitigating side channel attacks which exploit contention within the DRAM memory controller without resorting to static partitioning. At a high level, we introduce a memory shaper to shape requests to a representation called a directed acyclic request graph, something we call an RDAG. The shaper uses this representation to shape the timing of the victim's memory requests to a secret independent pattern. By doing so, our mitigation scheme, called DAGguise, is the first scheme to achieve formally verified security, while allowing for dynamic traffic contention and good performance. In this presentation, we'll first talk about memory controller and scheduler-based side channels. We'll then talk about existing approaches to mitigating memory controller side channels, through either static partitioning of resources or through traffic shaping. Then we are going to discuss DAGguise, our mitigation scheme, and in doing so, we'll take a brief detour to talk about directed acyclic request graphs. We'll then discuss our security and performance evaluations of DAGguise, and finally, we'll briefly talk about the generalizability of DAGguise to other scheduler-based side channels. To give a primer on memory controller side channels, we can first imagine the pathways that a memory request will take throughout the microarchitecture. A request will traverse from a CPU through the cache hierarchy before being serviced by the memory controller, which is shared by all CPUs on a system. This is problematic, however, as if an attacker simultaneously issues a request, their request may collide with the victim's, resulting in a visible latency caused by the controller's scheduling policy. This is a class of scheduler-based side channels, otherwise sometimes known as stateless or conflict-based channels. Such side channels are not limited to memory controllers. Any shared microarchitectural state managed by a scheduler may be vulnerable. Other examples include the L3, CPU ports, machine learning inference accelerators, GPUs, and many others. Now let's take a more concrete look at how memory controller side channels can leak information. One can imagine a scenario in which there is an attacker and a victim on separate cores, which both share the same memory controller. Depending on some Boolean secret, the victim will have a different DRAM access pattern. If the victim's secret is 0, it will perform no DRAM accesses, while if its secret is 1, the victim will access the DRAM a single time. While an attacker cannot directly observe the victim's accesses, it can access the DRAM at regular intervals and observe whether any of its own memory accesses are delayed. In doing so, it is able to discern the access pattern of the victim and thus determine the victim's secret. Let's now examine how such memory controller side channels have been addressed in the past. The first approach has been to statically partition memory controller usage through a round-robin, no-skip arbitration policy, such as in fixed service. Fixed service statically partitions and pipelines the memory controller such that memory requests from different security domains do not collide with one another, ensuring that no leakage occurs across domain boundaries. This static partitioning is secure, but of course brings significant performance penalties. If one security domain requires more bandwidth than another, such a scheme can have severe negative impacts on system-wide performance. On the other hand, an approach that is more general and less rigid can be found in traffic shaping. The strategy for traffic shaping is to delay existing requests and add fake requests, such that the victim request patterns look indistinguishable from one another. Consider our previous leaky example. What traffic shaping can do is insert a fake request, a request that goes to memory but isn't associated with an actual victim request, making the observations seen by the attacker identical. This is great, but it begs the question of how this is done for actual programs with complex access patterns without incurring a significant performance penalty. A state-of-the-art traffic shaping approach to mitigate such side channels is found in camouflage. Camouflage's traffic shaping strategy is to shape memory requests to a secret independent timing distribution by delaying real requests and issuing fake requests. First, one measures the timing distribution of the inter-arrival times of the memory requests issued by the victim during an offline phase, and then shapes requests to the secret-independent distribution during an online phase. This is an interesting approach, since it allows for dynamic sharing of the memory controller, allowing for contention between co-running applications rather than enforcing strict isolation, as in fixed service. Camouflage's approach, however, is insecure, since the ordering of memory requests and the request's bank information can reveal the secret. There's also the very significant problem of the profiling required by Camouflage. Camouflage relies on an inter-arrival time distribution, but in practice, this distribution is dependent on co-running applications. If a different set of programs with different memory bandwidth requirements are running alongside the victim's requests may be delayed, and in turn, its ideal timing distribution will also change. This makes it very difficult to profile victim applications, since we need to know the bandwidth requirements of all co-located applications in advance. Our work, DAGguise, employs a different traffic shaping strategy. DAGguise shapes memory requests to a secret-independent directed acyclic request graph, something we call an RDAG. And in doing so, DAGguise is able to ensure security, attain good performance by allowing dynamic traffic contention, and does not have the same profiling issues as prior traffic shaping works. To understand how DAGguise works, let's first discuss what an RDAG looks like. An RDAG is a directed acyclic request graph, which has vertices and edges. The vertices in this graph represent memory requests which are sent to a memory controller. These requests encounter a variable amount of latency, depending on the contention that they encounter within the memory controller. The edges between vertices represent fixed timing dependencies between requests, where the destination request can only be issued a certain number of cycles after the previous request completes. Consider requests sent between a shaper and a memory controller, which correspond to an RDAG. The first node of the request graph, V0, will be sent to the memory controller, and it will be marked as dispatched. The memory controller will finish serving the request a variable amount of time later, and will return a response to the traffic shaper. After 5 cycles, V1 can then be issued, and similarly, after 10 cycles, V2 can then be issued. All of these requests can contend with one another, in addition to other applications requests, while still maintaining a rigid structure, enabling security. So now you might be wondering why our RDAG formalism would be helpful in designing a defense mechanism. RDAGs help us achieve 3 goals. First, RDAGs help us achieve security through shaping any memory request pattern into a secret independent one, making the request patterns of a victim indistinguishable from one another to an attacker. Note that defense RDAGs are public and are the only thing that an attacker can recover. Second, RDAGs accommodate for dynamic sharing of memory resources in the memory controller, allowing for increased performance over static partitioning. Finally, the variable nature of RDAGs allow them to be versatile to varying levels of observed contention, avoiding the profiling issues encountered by Camouflage. I'll now pass it over to Yuheng, who will go into more details about each of these 3 points.
Let's look at security first. This is a very simple example to see how the different victim request patterns are shaped to a same defense RDAG to achieve security. We use 2 original RDAGs to represent the original secret-dependent request patterns. If secret 0, it sends requests with a 100 cycle dependency, and if secret 1, it has a 200 cycle dependency. We want to shift them into the same defense RDAG pattern, which has 150 cycle dependency. The right figure will visualize how the shaping happens with the timing representation. The time increases from the left to right, and you can see originally requests are sent out with 100 cycle interval. We want to shape it to a 150 cycle interval. How to achieve this? We can simply delay the second request in a buffer for 50 cycles before sending it out. The next request will arrive at the buffer after 100 cycles and be delayed for another 50 cycles before sending out, and so on and so forth. The shaping can be a little trickier for the secret 1 case. There's no original memory request to match the second shaper output, so we'll generate this as a fake request, and then delay the next original request for a long time to match the next shaper output, and so on and so forth. As you can see from this example, by delaying requests and generating fake requests, our shaper output is always the same, no matter the secret. This scheme helps the DAGguise system achieve very strong security. We further formalize the security property we want to achieve as indistinguishability property. I will first introduce the definition of this property in DAGguise system and then explain how we verify it. Here's our DAGguise system. It will get input requests from victim and attacker CPUs. The victim's request will be shaped by an RDAG shaper. The request will then contained in the memory controller, and the memory controller will generate responses to the victim and the attacker. The secret here is corresponding to victim's specific request pattern, and the attacker will try to distinguish victim's different request patterns based on its own observation, which is attacker's response pattern. So intuitively, we would like the attacker's observation to be independent from victim's request pattern. We call this property indistinguishability property. We further show that the indistinguishability property actually means two aspects. Firstly, it means given an attacker's request pattern, attacker has an identical observation when contending with any victim's request pattern. The table below will visualize this property. The row here represents a given attacker's request pattern X, and it will contend with different victims' request patterns A, B, C, which is represented by different columns. And this property is saying that when attacker is contending with different victims' request patterns, it will always observe the same response pattern. The second aspect of indistinguishability property is that we need this property holds for any attacker's request pattern, meaning that it is secure no matter what attacker strategy is being used. Again, we visualize this property in the table below. You can see that when the attacker uses other request patterns such as Y, it will still observe an identical response pattern. Here's an overview about how we formalize the property and verify it. We formalize the indistinguishability property using state transitions. We verify this property with Rosette. There are two steps in our verification. We first verify the property holds for the first k cycles of simulation with symbolic execution. Then we verify its holds for an arbitrary cycle with k induction. You can find more details in our paper. Now that we've looked at how DAGguise achieves security, we can additionally see how DAGguise achieves good performance, which is benefited from RDAG's adaptivity. We'll use the same example as before, where a victim has different request patterns based on a Boolean secret, and DAGguise shapes them into a same defense RDAG which has 150 cycle dependency. We will now particularly look at the contention of victims' shaped requests with an unprotected program. The unprotected program has two phases. In the first phase, it accesses memory infrequently with a 300 cycle dependency, and in the second phase, it accesses memory more frequently with a 25 cycle dependency. We can also ignore the original RDAG because only the victim's shaped requests matter. The red figure will visualize the contention. In the first phase, the shadow red means the unprotected program is delayed due to contention. Since the unprotected program accesses memory infrequently, the victim's shaped request can be issued without being delayed. During the second phase, the unprotected program accesses memory very frequently with a 25 cycle dependency. Due to contention, the victim's shaped requests are delayed, which will increase the request interval from 250 cycles to 325 cycles. From this example, we can see RDAG's adaptivity allows programs to contend at memory controller and achieve better overall bandwidth utilization. Compare this with static partitioner schemes, which would have a static request interval and cannot adapt according to the contention. Compare this with camouflage, which has to reprofile the request interval with the new phase of the unprotected program. Now, let me pass it back to Peter.
DAGguise employs an offline profiling step, which constructs a defense RDAG which optimizes for performance. Note that shaping to any secret independent RDAG will ensure security. This step is only for performance reasons. Opposed to other shaping mechanisms, DAGguise's profiling costs are very low. Thanks to the adaptivity properties of RDAGs, we only need to profile the victim application alone. To construct a defense RDAG, we search for parameters to use in an RDAG template, decreasing the search space of potential defense RDAGs. On the right, we show an example of such an RDAG template. This template has 4 parallel accesses to different banks, and our profiling step determines the fixed latencies. More details about the offline profiling step are included in the paper. Our performance evaluation consists of a GEM5 and DRAM Sim2 model simulating 2 and 8-core CPU environments. We evaluate the performance of the DAGguise shaper and compare it to fixed service and insecure baselines. We measure the normalized system-wide IPC of unprotected spec benchmarks, which are co-located with DAGguise protected example applications. Here are the experimental results for the 8 CPU setup. We note that DAGguise improves upon the system-wide performance compared to fixed service across the entire system, increasing the IPC of unprotected and protected applications. Specifically, we observe that DAGguise achieves a 12% performance improvement over fixed service. We also note that both RDAGs and DAGguise can be generalized to more scheduler-based side channels. For instance, both SMT cores and network-on-chip routers have schedulers which can exhibit visible contention between an attacker and a victim, resulting in leakage. The principles from DAGguise can be used to shape requests corresponding to an RDAG representing either case, again allowing for dynamic contention in these structures while maintaining security. Please see our paper for more information about the implementation details of the DAGguise shaper, the formal security verification using symbolic execution and K-induction through the Rosette solver framework, more information about the RDAG offline profiling process, more performance and area evaluations, and further generalizations to other scheduler-based side channels. In conclusion, we present DAGguise, a memory traffic shaper which completely eliminates data leakage, allows for dynamic traffic contention, and requires only simple profiling. We additionally introduce directed acyclic request graphs, something we call RDAGs, a general and adaptive request representation. Using Rosette, we formally demonstrate that DAGguise is secure, and we show that the principles of RDAGs and DAGguise can be extended to many other scheduler-based side channels. Thank you.